Okay, so I'll give you a brief overview of upcoming support for stochastic differential equations. So I worked for the kernel group for 8 years. So let me try first as kind of picture my talk as a continuation of Rob's talk, right? So what is a stochastic differential equation? It's typically painted as you have an ND solve, and then you take that system which is described by particular dynamics and you perturb it with a noise or something which is beyond your control. So typical example of it would be a small particle suspended in a fluid, and it will be hit by the fluid molecules and will experience a chaotic motion. So few things to notice is that it's in this particular case are continuous trajectories. They are jagged, so they are smooth but probably non-differentiable. And if you were to sort of look at the particle over and over again in parallel universes, then you'll see that those trajectories would actually be different every time you repeat the experiment. In other words, they are random. So the examples of models like this would be like, say you have a pendulum and the length of that pendulum would change stochastically over time, or you have an epidemic dynamics and say susceptibility of individuals is again random, somehow changes and so on. Or in other words, you'd just have your model and you would add a random variable in there or some sort of a noise. Now, the way we model the things is that you would, in a discretization of time, you'll just say that the difference between a next state and a current state is given by a dynamic, some function of your state times dt. This is a sort of a holy grail of the science, right? This is Markov processes, but then you would add a noise to it, and whatever that noise means. So at each moment of time, you are perturbing a system by a noise. And looking at the random walk and borrowing from a random walk, we'll just take that noise to be a small perturbation, and that perturbation would be a difference of two processes, namely the Wiener process. Now this is all hand waving, and actually this whole thing started to be sort of developed in about 1905 or with Brown actually describing the event, and then Einstein describing the displacement and average absolute value of this displacement. But it was put on a rigorous footing much later by essentially Wiener and Ito later. So a rigorous way to define this process would be to say that you have your x of t, value of your process at time t is given to its initial value plus a Riemann integral, where in here this is a function up to time t, so presumably known the trajectory of a process, and you are performing a simple integration. So if you have a function which is jagged, there is no problem with you integrating this using ND solve. But then there is a new N integrate. There is a new ingredient called Ito integral, and the meaning of the process will depend on what we mean by an Ito integral. So a contribution of Ito was to actually put this on a sound basis. So what he says is that Ito integral here of a particular function of your process times dw, and you should contrast this to what I said on the previous post, is that noise is given by a difference of wt's, and this difference becomes kind of a dw. So what this means is that the probability limit of a Riemann sum. So in this Riemann sum you evaluate your function here, and then you multiply it by dw, right? It looks very much like a Riemann sum in the definition of integral. However, there is this problem with the probability limit, is that if you actually try to evaluate the sum, you'll find that the limit doesn't exist. It can be any number on a real line. But the thing is that this any number, it might have a sensible distribution associated with it, and this is what this probability limit means. It means that if you repeat over different things, so you will be able to assign certain probabilistic law to this many possible outcomes of this limit. Now this just simply tells you that the Ito integral really is a random variable rather than a number. And the x of t, which is the value of your process, would be again a random variable. So you should look at any sort of process as essentially an infinite collection of random variables, which if you look at time 1 and at time 2 and at time 3, at each of these times is random variables, and they will in general be correlated. Well, there will be some dependence in them. So this Ito integral has some remarkable properties, namely it has zero mean no matter what you integrate, assuming that expectation does exist. And it also has this additional property called Ito isometry, which is technically useful, but I wouldn't go into its detail. Now, the zero mean property means that if in this particular differential equation you don't have the a is equal to 0 and you have so-called no drift, then you have the process which you take the expectation, and expectation of this guy is going to be an expectation of that guy, because Ito integral has 0 expectation by default. And this property goes by the name of a martingale. There is a big deal because the martingales are very effective instruments in the probability, so and also martingale plays an important role in finance. So Ito processes turn out to be a very nice probabilistic instrument. So we will start by giving an example of an Ito integral, which is a w of t dw of t, and try to simply evaluate that. So we will start by generating using the random function to generate a realization of a Wiener process, and it gives us a temporal data. We can extract states, right? So this would be a state at time 0, next state, and so on. And we will try to form this exact definition for the discretization, and we will get a number out of it. So this will be our approximation to an Ito integral. We will code this up, and then we will try to repeat different trajectories of a Wiener process to get these numbers out, and see how, depending on the value of your discretization, the resulted distribution for the Ito integrals approach some limit. And you will see that if you take a step to be very small, very big, then that agreement is not very good, because you see some checkedness. But as you decrease age, the agreement becomes better and better. So in other words, in distribution, your Ito integral converges to a random variable, and that random variable is known in closed form. So in here, we are just doing the same things, and now computing so we are repeating computations of Ito integrals 5,000 times, and for each Ito integral we evaluate a value, and then we compute the mean of those values. So we compute the mean of those values, and we get a number which is close to 0, and we should compare this to an exact result which is exactly 0. And here we are illustrating an Ito isometry where we compute a variance of the Ito integral. We get a number of 0.5, and the exact computation tells you that it has to be exactly 1/2. So this sort of just boosts the confidence of what now we mean by an Ito integral, and now we are sort of ready to say what an Ito process is. So suppose you just have functions a and b, which are which are some functions depend on either x itself, in which case it would be a differential equation, or they depend on some known process. Right? And in that case, we just say my x of t is going to be given as this collection of random variables. Sometimes it's written in a differential form. In a differential form, this is just the same thing written this way. Okay? Just to parallel it. And now in Mathematica, we can input an Ito process in several ways. One of them would be to just give the essential, namely the drift and diffusion coefficients, the initial value and the initial time value. Or you can you can proceed one more step and actually specify the output. So that is, you have a process which describes x of t, but in the output you actually don't want x of t, you want a logarithm on absolute value of x of t. You are able to specify that. Or you can just reiterating what Rob said, that it's nice to be able to support equational input. We try to go some ways to support that, and we can specify a differential equation for the Ito process by giving this drift and diffusion coefficients in an explicit form. You specify these differentials, and then you have to say this W is a Wiener process. In principle, you can give any other Ito processes in there, and the system will automatically chain that. So let me give you some examples. We have several named parametric processes, and you can wrap Ito process around it, and it will give you an explicit representation for it. So for Ernstein-Uhlenbeck, you have a drift given by this linear function, and the diffusion is constant. Right? So here is a Brownian bridge process. In this process, the drift coefficient is actually time dependent, so this is time inhomogeneous process. This is a process with an output. You have a Wiener noise with 0 drift and unit diffusion, but you have a non-trivial output. Notice how Mathematica parsed this and automatically attributed b understood b as a function, because b was specified as a state of the process. And you can also use an equational input to specify an Ito diffusion differential equation, and then Mathematica understands that as well. Now, Ito integral, of course, is considered just a special case of an Ito process, because an Ito integral is a driftless, so drift is 0, and so the Ito integral we were considering earlier would be entered through the Ito process just like this. So that's WDW. Now let's move on and actually say something about why Ito's framework was so successful. So you have an Ito process which is defined by a particular differential equation, and then this class of processes has a nice property that if you take a smooth function and evaluate a smooth function of your Ito process, this resulting random variable, or random process rather, is again an Ito process, assuming that your function is good enough. And well, the way to connect to find out a new drift and diffusion coefficients for this sort of compound process is known as an Ito formula. So let's define an Ito process, and when so it has a non-trivial output here. You see arbitrary function f. Right? And it also is specified by using arbitrary diffusion, arbitrary drift coefficients. I'm sorry, drift and diffusion. Now, if you apply an Ito process to it again, it will flatten the output. So it will make it into a standard Ito process where the output is one of the variables, one of the state variables. So let's try to do that. And you see that it introduced a variable formal x1 here, and it put that variable in the output. But for this variable, it computed the drift coefficient. Here's this expression and a diffusion coefficient. And this combination, so namely this formula for this coefficient, for that coefficient is collectively known as an Ito formula. Okay, Ito formulas are extremely instrumental, in doing various things. So, for instance, you can take the process we looked at previously. So that's a WT for Wiener process squared minus t, and try to evaluate the Ito process of it again to apply a Ito formula, and you see that this new variable, which the y variable, actually has 0 drift, and that means it's a martingale, right? So because it's a martingale, it has some nice properties, and actually many textbooks exercises will give you a process, a certain function of a process, and ask you to verify whether it is a martingale, and the Mathematica can be instrumental in answering these questions. So let me proceed further on and introduce another thing which is often seen called Stratonovich process. So this just tells you that the way to set up the processes is not unique. So in addition to Ito, you can define a Stratonovich process by simply replacing Ito integral with a Stratonovich integral. And a Stratonovich integral is just a different way to assign a random variable to this. And notice what you do, you just almost do the same, except you sample your function that you are integrating at the midpoint of your time interval from ti to ti plus 1 instead of at the beginning as an Ito integral. Well, the result of it is, so you might ask, why would you go to such a pain? Well, there is a good reason for it, and that reason comes in basically what the Ito formula for the Stratonovich process would look like. So let's define again a generic process with a generic drift and a generic diffusion and a generic output. So, and apply an Ito formula, sort of try to make it into a standard thing. And you see that the new drift and new diffusion just are computed using the ordinary chain rule. And this makes it extremely easy to do certain computations on the manifold or whatnot. So this has its own applications because the calculus formula sort of carries over. And well, there is the Stratonovich process and the Ito process are actually interconvertible. You can take a Stratonovich process and write it in the Ito form. So here is a Stratonovich process with a generic drift and diffusion, and you can convert it to an Ito process, and you see that the Ito process has the same diffusion, but the drift is shifted by a derivative of your diffusion coefficient here. And you can now convert back, and it recovers you back this Stratonovich process. So in a sense, this is a kind of trivial process, but because it's recoverable from an Ito process. But on the other hand, it's useful in one instances over the other. And here is an example of it. So you can take an Ito process of a geometric Brownian motion, and that looks like a familiar process with a linear drift and linear diffusion. And you can convert it to a Stratonovich, and you can see that it actually is not exactly the same. It looks slightly different. So now we might be asking ourselves, can I actually solve this stochastic differential equation for the geometric Brownian motion by simply representing the Stratonovich process as some function of a Brownian motion process? So if such a function does exist, then I can invert it and say that a Wiener process would be a function of a geometric Brownian motion. So I simply try to to build such a function. When I substitute it and apply an eta formula, I see that for the coefficient of this new variable, I see occurrence of this particular object, and I want to make it constant, so that means g has to be taken to be a logarithm. So if I apply the logarithm, I get this guy. And notice that for x1 variable, which stands for logarithm of the Stratonovich process, the drift and diffusion are constant, and you can obviously solve for that. So that means that this particular component is just a Wiener process. So log of a Stratonovich process turns out to be a Wiener process like this, and this way we found a well-known fact that geometric Brownian motion is actually an exponential of, you solve for this now, and the geometric Brownian motion is an exponential of a Wiener process. So enough theory, right? Let's actually do some examples, and to do such an example, I took actually something quite simple. We have a damped harmonic oscillator, and let's make the proper frequency here stochastic. So we'll make this into W0 squared plus some white noise added to it. We write it up as an eta process, and in order to write it up as an eta process, we need to make this into a system of first-order differential equations. Sort of a bit of an inconvenience, but unfortunately there is an ambiguity a bit in automating this, but it's easy. So we just introduce a velocity, and we say dxt, so x prime is equal to velocity, right? But we write it as a dx equals to v dt. And so we just say v prime is equal to this guy. That's just a differential equation. But then we have this noise, this noise term here. So this means really that you've replaced omega squared with an omega squared 0 plus a noise term, right? And the noise terms dt is what this dw stands for. But notice that in general this is a linear system, right? So you expect you sort of expect an easy solution, but the reason I highlighted this is to just show that you have every increment in a normal variable, in a Wiener noise, you have it multiplied by the stochastic process itself. So if you multiply a normal random variable by a new random variable, typically God knows what you get, but you don't get anything simple. So this means that if you were to look at the value of this eta process at any time t, this is not going to be a normal random variable. It's going to be some random variable. So this means that typically you wouldn't be able to compute this in a closed form like a PDF or anything like this. So one thing we've added is an ability to automatically compute a mean function and a covariance function whenever possible. And this is an example of a non-Gaussian process where such a computation is possible. And we actually can ask for Mathematica to compute a mean function for this process at time t. And you get actually to see that this is exactly the solution of a classical system where sigma is equal to 0. And this is manifested in the fact that it is not dependent on sigma at all, on the variance of your noise, right? So if you set your variance noise to 0, you'll get a classical system back. So this is a classical solution. But you can actually compute a variance as well, and you get for this nasty complicated thing back is for the variance. But if you take this variance and replace, send sigma to 0, and actually do a simplification on this, you will get that the variance is exactly 0, inspiring us actually some confidence that this is really a meaningful result, right? This is what we expect. So this is a cross-check. Now we can do a simulation of this. So we just take a process, put in some parameters for the damping coefficient, proper frequency, initial value, and the sigma. You get this, you simulate it. You simulate it using a particular discretization method called Clayton-Shorts, and we get 8 trajectories, and now we visualize. And the visualization, of course, is a lot more complicated than that, but I just hid it. And so what you see is that you have these trajectories which are written in gray. The red line is an expected, is a mean function. The band around it is a mean function plus or minus the standard deviation. So it sort of tells you that a sampling of your process, so that's random realization of a process, follow up the mean plus or minus some randomness in them, and they look like this. So what we are about to include in version 9 sort of allows you to do some limited analysis. But I wanted to also say that for graduate student, this functionality will actually be able to provide you with a facility to solve some problems. So say you have an Ernst and Uhlenbeck problem. This is a problem I borrowed from a Stack Exchange where students ask for help with their homework problem. So this was one of the problems. You have an Ernst and Uhlenbeck process, which implies that you have some stochastic differential equation behind it, and then you want to compute define for this process an associate process, which is a time average, right? So you integrate the process from 0 to t, and then you divide over t. This is a time average. This is a new process. And now you want to compute a cross covariance. That's a covariance of x of t and y of t. And you want to compute that in closed form. That's what the process asked. Now, how would Mathematica allow us to do this? So we define an Ito process. We have to specify a driving noise, and the driving noise in our case will be an Ernst and Uhlenbeck process. So we say Ernst and Uhlenbeck follows, OU variable follows an Ernst and Uhlenbeck process with these parameters. Now we say dx is equal to DOW, which is really to say that x is really OW process, right? But dxa, that would be xa variable, or dy, that's what I should probably have called it. So dy is 1 over tau x t dt. That's what is written here, right? Now I evaluated and I'm asking for a covariance of this process, and I'm looking for the 1 and t component, which will be a cross covariance. Oh, great. Oh, thank you. Thank you. So there it will think for a second, being on the batteries, and will get you a nice result. That's a small result, which explains why this is a homework problem, right? So, but this is like a benchmark, really. If we are able to solve a homework problem, then what we're shipping is not really a complete garbage. So, right? So let's then try to proceed with more problems like this. So we would have a Wiener process squared, and we integrate it over time from 0 to t. Okay, I'm running up. So we define it as an Ito process. We ask Mathematica to compute a bunch of moments. That's from 0 to 12, and we are able to compute it in closed forms. We set this up as a random function. We simulate it, and we are able to verify the moments of a compute. So we generate 10,000 trajectories, and we compute descriptive moments and compare them to the moments of this evaluated at time t, and you will see that actually they come out to be pretty close to one another. That's you can see that now, and I'll interrupt that to try to wrap up. And this is more juicy. The Heston model is something that's used in finance, and it describes you an evolution of your prices and involves a volatility, which is stochastic itself. So you define the equations for volatility, define equations for prices, and this is just like a geometric Brownian motion, and you are able to simulate it. Say you generate 6 paths, and then you do just a visualization of this. You see how the prices vary, and you see some visualization of a rate, how rate changes in time, and you can do some simulations with that as well. Another thing, which is, if I'm running really out of time, I wanted to say that very often when you do a discretization, you can run into trouble. So here is an example of a process where diffusion coefficient has a limited, it's only supported on the interval 0 and 1. And if you do a discretization, you can actually get into a problem where you will step outside of that interval. And when outside of that interval, the argument of square root will become negative, and a square root of a negative number will give you a complex number. And this is manifested in having this small imaginary part in the mean. And this is something you want to avoid because it can lead you into problem. And we have a way for each method of a simulation to specify a projection function, which will take your approximation for the next step and project it back into where it needs to be. So in this particular case, it's a clip. And you can see that after that, the mean value is completely real. And this is a visualization which shows why this process is interesting, because its stationary distribution is uniform. So you start with some initial value. In our case, the initial value is 1/2. So you start with a step function as a CDF, and as time progresses, this CDF function levels out and becomes a straight line, which means that the steady state distribution is sort of uniform. So let me move on, and actually the last time is an accuracy on approximation schemes. So random function supports 4 different methods for simulation of Ito processes. That includes stochastic Runge-Kutta methods, familiar Milstein, Euler-Murayama, and Claude-Clayton-Shorts for scalar noise. So here I'm just simulating this process, and I'm computing for this process the standard form. I'm simulating it. I'm getting out the value of this process and the value of a Brownian motion, and now I'm computing residual. So for a value of the Brownian motion and a value of that process, I'm computing the process minus what its expected value, and I'm plotting the histograms of these various distributions. So you see, for Euler and Murayama, the expected residuals are pretty large. If you increase the order, so this is a convergence of square root of step size. This is just a step size, so that's order 1, and you see that the residuals are now much smaller in scale. If you use a KPS method, which is order 1.5, you see that the residuals are now smaller in at least one order of magnitude, so this is more of an accurate model. And at this point, thank you. I'm already running out of time.